Next speaker is Jack Koolen from Department of Mathematics at POSTECH in Korea. Optimal realisations.
Okay, thank you very much. I continue where Andreas Dress left. I mean, I'm sorry it will be as abstract as his talk. I already apologize for that. So, okay. So what I will do is I will first look at optimal realizations, and then I will look at time spans, and then I will look at metrics on 4 and 5 points. 4 and 5 points sounds very little, but what turns out that even on 5 points we didn't really understand the metrics yet. So we know already what is a metric, so I will not do that. So Andreas Dress had already the talk about graphical realizations, and that is what I will talk about in this talk about. So I will the idea will be okay. So if I have a metric D, then I can always make a realization. And what you do is take the graph C, where you take all the edges between the elements in X, and put the dxy as the weight on the edge xy. And now what you would like to do is to take the realization with minimal number, where you sum over all. Suppose you have a realization, then you can look at the sum of the weights of the edges, and then you want to take that sum as minimal over all realizations of your metric. This sounds like a good thing to do. I mean, okay, so one way you can get realizations is by proximity graphs, and that says so Andreas Dress has so we can look at proximity graphs, and that is where you look at the edges instead of the click where we did before. We had the set X, and we put between every two vertices the edge. But now if there is a vertex between the two X and Y, say Z, that the distance between X and Z plus the distance between Z and Y is really X and the distance between X and Y, then you don't have to put in your edge X and Y, because that is already realized, that distance. So that is how you can define proximity graphs, and they are reasonable. They give a lot of information on your metric. Okay. So why do you want to look at realization, optimal realizations? Is because of tree metrics. So we want to, to construct the phylogenetic tree, you want to find a tree which approximate your distance as good as possible. So, and of course, if you start with a tree, then you want to find the tree back. So what Boeneman showed is that you can show that a metric is a tree metric, so the optimal realization is a tree metric, if and only if the maximum of the three distances, the sum of the three distances, xy plus uv, xu plus yv, and the distance xv plus yu is equal to the second lastest. The two lastest distances, some pair of distances, are equal. So, and as I already said, Andreas has already showed that if a metric is a tree metric, then its optimal realization is a weighted tree. But usually the distances you obtain from biological data does not usually give a tree. So one way to avoid to find the tree is to find its optimalization, and if it's a tree metric, you will find back your tree metric or your tree. So that sounds like a good strategy. But there's some problems, and the first problem is that it is NP hard to find the optimalization. So how can you show that? Andreas Dress showed in 1984 that if you have a metric with n vertices or n elements, then you can any optimal realization, I have to say non-degenerate, because we don't want to put in vertices of degree 2. Otherwise we can put as many as we want, infinitely many if you like. So that is why we have to assume non-degenerate here. But if you assume it's non-degenerate, then you may assume that the number of vertices is at most n to the power 4. And then Althofer and Winkler, both independently in 1988, showed that to find whether a rational metric, to find the optimalization is NP complete. That it is in NP follows from the result by Dress, and that it is NP, the completeness was shown by Althofer and Winkler. But there are some more problems. Andreas Dress already mentioned that some metrics have already 2 optimal realizations. So if I look at this metric, where you see that one over here. Okay. If you look at this metric, this means that the distance between x and y is 4, the distance between y and u is 2, and so on. Then that has 2 optimal realizations, namely this one and this one. They look very the same, but the difference is that the u and v are interchanged, so they are really different. Okay, and then there was another problem, that you cannot have only 2, you can have infinitely many different ones. So there was another problem. So what you can define, if you have given a metric x, d and a graph such that the vertex set contains x, and then you can ask yourself what is the set of weights on this graph such that this gives an optimalization for your metric. And in Althofer in 1988 gives an example where this set SDG is not finite. What you can show easily is that this set is a polytopic complex. I will not go into detail what that means here. But I don't know any example where this set is not convex, and probably it is always convex. But one of the hopes we have is that almost all metrics have a unique optimalization. So that would give some motivation why you should look at optimalizations. Okay, so as Andreas Dress already mentioned, there is something called a tight span. And I define it slightly different than he did. I define it as the functions such that there x, for all x there is a y, so that fx plus fy is equal to fxy. And for all x and all y, fx plus fy is at least the distance between x and y. And the tight span was first introduced by Isbell and later discovered by Andreas Dress and other people as well. In the context of Andreas Dress for finding the phylogenetic tree, and others to find some problems in computer science. But the tight span is usually not a convex polytopic complex And what you can show is it consists exactly of the bounded phases of the polytope X, D. The generic tight span on 4 points is this picture. So you have 4 vertices, and then that is it. Yes, that is what it looks. So you have one phase of 2 dimensions. So you have 1 2-dimensional phase, and this is like this, and then you have 4 edges, sticking out edges. And what you can do is you can show that your original metric is isometrically embedded in the tight span. That is done by the Kuratowski maps as shown in this slide. Okay. So what has this to do with 4 and 5 points? So we have seen the tight span on 4 points. So let's look at that one more time. So the tight span on 4 points was like this one. And if you remove, so you have this the tight span on 4 points is like this one. And if you the interior of that 2-dimensional phase, then you get the optimization of this metric. So that is how it works with 4 points. But for 5 points, there are 3 generic tight spans on 5 points. We call them type 1, type 2, and type 3. But there are also something like 3 generic optimizations on 5 points, namely this kind of optimization, this kind of optimization, and this kind of optimization. And then you say, yeah, so type 1 must correspond to type to the first one, A, and type 2 maybe to B, and type 3 to C. But so easy, it is not that easy as this kind of correspondence. Doesn't work like that. It was quite surprising that it didn't work like that. So the first generic metric of type 1 always have an optimization of type A. So that was okay. But for the second one, okay. That was also quite okay. For type 2, there has an optimization of type 2, always. But some of them, as I have seen already before, may have different ones. But then the surprising one is that for type 3, I'm sorry, here's a misprint, this will be type 3. But any metric of type 3 can have optimization of type 2, B, and of type C. And some even have both of them. So that was very surprising for us. So the first one goes to A, the second one goes to B, but sometimes this part is flipped 90 degrees, so sometimes it's like this one. And then you have type 3C, and that is this one. So type 1 goes to A, type 2 goes to B, which maybe sometimes flipped. But type 3 goes to B and C, so that was the surprising part of this. But that was and then there's something. What was also surprising is let's just skip this. One other thing is that follows is that usually for every metric on 5 points there is a unique optimization. There's only very few of them which have more than one optimization. So that still works. So almost all metrics on 5 points have a unique realization. So we have some hope to show it for any n, but thank you for your attention.
You have mentioned 5 points. There's 3 types of genetic dimension. How
Yes.
they look like?
The three types, yeah, but that is not so easy to describe. You mean type 1 and type 2, type 3. Type 1 looks more or less like type A, yeah, but type 2, yeah, that is not so easy to describe. I can show you later in some.
Are there other questions?
How much time did you spend trying to prove this one?
The conjecture whether there is quite a bit of time.
So do you think you will prove it eventually?
I hope so, but I'm not sure whether it is really true. I mean, now we are trying to work out for 6 vertices, whether it's true for 6 vertices, I mean, that kind of thing.
Are there other questions? Well, let's thank Jack again.